Welcome to our YouTube channel. This is Ernest coming to you from MathLab Tutorials in Toronto, Canada. Although seemingly impossible, like many other contributors on YouTube, our mission is to transform some of that destructive hate energy into constructive love energy for a subject that is so deserving. Mathematics is part of all that surrounds us. Just pause for a moment and take a good look. As your screen suggests, like it or not, math really did take us from the Stone Age to the Space Age. The sermon is over, and now let's get down to some serious math. This is video 6 of the video series on radicals, and I will show you how to solve simple one-radical equations. Some notes first. I have developed a general technique for solving simple radical equations, and let's look at this equation right here. First of all, it really is an equation because we have an equal sign, and you'll notice I put a 0 on the right hand side. That's normally called standard form, and on the left hand side I have a, b, and c, and b has a square root on top of it, so that's why it's called a radical equation. Now normally we assume that a and c do not contain square roots, so a and c are radical free, and the only square root appearing is that square root of b. We'll also assume that a is an expression containing a single variable, b is another expression containing a single variable, and c is a third expression containing a single variable. So altogether, this equation will constrain the values of x that will actually solve it. Okay? And if we look at all possible values of x that will solve this equation, then we call that the solution set for the equation. So I identify that as equation 1, and we'll call it a simple one-radical equation. Again, we only have a single radical. We have an a, which is radical free, c is radical free, but now we need to impose some conditions. We know that b has to be greater than or equal to 0. That's just the argument of the square root. Because if b were negative, for example, -1, then the square root of -1 is imaginary, and this equation would not be a real equation. It would be a complex equation. So we don't need to deal with that right now. So we impose that b is greater than or equal to 0, and that's to ensure that the equation is real valued. Next, in order for this equation to have a solution, the two terms must have opposite signs. Okay, the two terms must have opposite signs. Like, for example, this should be like the a should be positive and then c should be negative. Otherwise, there's no way the two positives can ever give you 0. Likewise, if a is negative, c should be positive. Otherwise, there's no way you can get 0. So we need the a and b to have opposite signs. The way we say that they have opposite signs is that their product, a dot c, is less than or equal to 0. Okay, this just means that when the product is less than or equal to 0, you know that a and c have to have opposite signs. And that's to ensure that a real solution does exist. Okay, so beware of these two conditions. B has to be greater than or equal to 0. That's the argument of the square root. And a and c have to have opposite signs. So that means that a dot c is less than or equal to 0. Okay, so keep those ideas in mind, and we'll go to the first slide. Here are the general steps for a solution. The first thing we do is transpose the c over to the right-hand side. You'll recall that the c was on the left. We're going to move it over to the right. When we move it over to the right, we get a dot the square root of b is equal to minus c. That's the first move, is to transpose the c over to the right. Once we do that, the next move is to do an SBS. SBS means square both sides of the equation. Okay, so when we square the left-hand side, we get a squared dot root b. Root b is just b, so we get a squared dot b. On the right-hand side, minus c all squared is just c squared. So minus c all squared is just c squared. All of a sudden, we notice that the equation is radical free. Okay, but this squaring process that we have to go through in order to solve a square root type equation is likely to introduce extraneous solutions. In other words, we might get candidates for solution that are in fact not solutions at all. And that's typically what a squaring process does when you're trying to solve an equation. Okay? The equation becomes more general than the original equation. Okay, so be aware of that. You start off with an original equation. At some point when you square both sides, the new equation that you get is not equivalent to the original equation. Okay, be very careful about that. The original is not equivalent to the one where you square both sides. In other words, going back, this equation over here is not necessarily equivalent to this over here. Okay? You may introduce solutions that are in fact solutions of this equation, which is the squared equation, but not the original. Okay? So we have to be careful with that. Anyway, at this point, this equation over here is radical free, and we're all happy about that because we hate radicals. And at this point, step number 3 is to use algebra to solve the radical free equation. Of course, that's this one up here. We can use algebraic methods to solve this. And when we solve this equation over here, which is the squared equation or the radical free equation, we get solution candidates. Okay? Now the last step is to substitute each solution candidate into the original equation, equation 1, to verify that the left-hand side is indeed equal to the right-hand side. Okay? If you set the left-hand side equal to the right-hand side, it may turn out to be true, and that means we accept the candidate as a solution. Again, when you set the left-hand side equal to the right-hand side, it may turn out to be false, in which case we reject the solution candidate. And the reason why we get rejections is due to the squaring process. Okay, so be very careful with that. So let's go on to the next slide. And we're going to go through some practice problems here. Question number 1, solve and verify. And do not forget to verify. Okay. Note the square root of a is equal to minus b as long as a and b are greater than 0. If that is the case, okay, this type of equation will never have a solution because by definition the square root of a is positive, and if a and b are both positive, then the right hand side is negative, and there's no way that a positive left-hand side can be equal to a negative right-hand side. There's no way that that can happen. You can't have a positive number on the left equal to a negative number on the right. So this equation, like this equation here, this radical equation here, can never have real solutions. Okay? And the reason is that the square root of a is greater than 0 and minus b is less than 0. So beware of that. Let's look at the first question. The square root of x is equal to 3. The first thing we want to do is square both sides. When you square the left-hand side, you get x. When you square the right-hand side, you get 9. And now we need to verify the original equation. And of course, that's the original equation. What we do is set the left-hand side equal to the right-hand side, and let's see what happens. You have the square root of x is equal to 3. You sub in x equals 9. On the left, you get the square root of 9. On the right, you get 3. And then the square root of 9 is 3. We have 3 is equal to 3. And of course, that's a true statement. So you declare the solution candidate, x equals 9, to be the solution in fact. Okay, so let's go on to the next question. Question 2, solve and verify. And again, do not forget to verify. We have the square root of 3 dot x equals 6. We have to square both sides. When we square the left-hand side, it removes the radical. That's the whole idea behind squaring both sides, is to remove the radical. So we have 3 dot x, and on the right, 6 squared is 36. Divide both sides by 3, and you get x equals 12. We declare that to be the solution candidate, and now we verify that the left-hand side is equal to the right-hand side. Again, we go back to the original. The square root of 3x is equal to 6. We sub in x equals 12. On the left, we get the square root of 36. On the right, we get 6. On the left, we get 6. On the right, we get 6. Obviously, this is true. And that means we can declare x equals 12, which was initially the solution candidate, as the actual solution. Okay? So 12 is the solution in fact. At this point over here, without verification, it was only a solution candidate. Why? Because we had to square both sides. Okay? So a solution candidate may or may not be a solution in fact. So let's go on to the next slide. Question number 3, solve and verify. Do not forget to verify. We have the square root of x is equal to negative 5. Well, you know, by definition, the square root of x is positive. And then on the right-hand side, we have a negative. And so there's no possible way that this can have a real solution. So, excuse me, we note the left-hand side is greater than 0, and the right-hand side is less than 0. That means no possible solution. But we can go ahead and go along for the ride, and we'll see what happens anyway. If you perform an SPS, that means square both sides. On the left, you get x. On the right, minus 5 all squared is 25. That's our solution candidate. And now we go ahead and verify. We do left-hand side equals right-hand side. The square root of x is negative 5. That was the original. We sub in x equals 25. And then on the left, we get the square root of 25. On the right, we get negative 5. On the left, we get 5. On the right, we get negative 5. Of course, this is a false statement. And so we declare that the solution candidate is, in fact, extraneous. Extraneous means it's just a candidate, but it wasn't the true solution. Okay, it's an extraneous solution. Okay, so let's go on to the next slide. Question number 4, again, solve and verify. Do not forget to verify. We have the square root of x plus 2 equals 5. Again, we're going to square both sides. On the left, we get x plus 2. On the right, we get 25. So you want to transpose the 2 over to the right-hand side, and we get x equals 25 minus 2, which is 23. That's our solution candidate. And now we need to verify the candidate. We put left-hand side equals right-hand side. Again, that's just the original equation. And it's always the original equation that needs to be verified, by the way. I hope you're clear on that. So there's the original equation right there. We substitute in x equals 23. On the left, we get the square root of 25. On the right, we get 5. On the left, we get 5. On the right, we get 5. Of course, this is a true statement. Therefore, x equals 23 is, in fact, the solution. Very simple. Question number 5. Again, solve and verify. Do not forget to verify. We have the square root of 3 minus 2x equals 7. Again, you want to square both sides. When you square the square root on the left, you get the inside, which is 3 minus 2x. When you square 7, you get 49. You move the 3 over to the right-hand side, and you get minus 2x equals 46. And then divide both sides by negative 2, and you get x equals negative 23. And that's our solution candidate. And next, we have to verify that the left-hand side is indeed equal to the right-hand side. Again, we go to the original equation, we copy-paste, and we substitute in x equals negative 3. And when we do that, we get 3 minus 2 dot negative 23, which is 49 on the left. So we get the square root of 49 on the left. We get 7 on the right. Square root of 49 is 7 on the left. And of course, we have 7 on the right. This is a true statement. So we declare that x equals minus 23 is in fact the solution. So we'll go on to the next problem. Q6. Solve and verify. Do not forget. This is another one of these little trick questions over here. We know that the left-hand side has to be positive, and yet the right-hand side is negative. So this cannot have a solution. No way. We already know that. But anyway, I made a note of this. The left-hand side is greater than 0, and the right-hand side is less than 0. That implies automatically no solution. There's really no work that needs to be done. However, we'll go ahead and do the work anyway. If we square both sides, we get on the left, we get 1 minus x. On the right, minus 3 squared is equal to 9. We transpose the 1 over to the right-hand side. We get minus x equals 8. Divide both sides by negative 1, and we get x equals negative 8 as the solution candidate. At this stage, we try to verify that left-hand side equals right-hand side. We grab the original equation, drop it down, and we sub in the candidate, x equals negative 8. On the left, we get the square root of 1 minus minus 8, which is square root of 9. And on the right, we get negative 3. So on the left, we get 3. On the right, we get negative 3. And of course, 3 equals negative 3 is false, and therefore, there is no solution. So that candidate that we got up here, which was negative 8, is in fact an extraneous solution. Okay? It's a solution to the squared equation, but it's not a solution to the original radical equation. Okay? It's a solution to the radical-free equation, but not a solution to the actual radical equation up here. Okay, so we can go on to the next slide. Question 7, again, solve and verify, and do not forget to verify. We have the square root of x plus 1 equals 0. We can go ahead and square both sides. We get x plus 1 equals 0. Transpose the 1 over to the right-hand side, and we get x equals negative 1. That's our solution candidate. And again, we verify that the left-hand side is equal to the right-hand side. We copy-paste the original radical equation. We copy it down here. And then we insert our solution candidate, which is x equals negative 1. And on the left, we get the square root of negative 1 plus 1, which is square root of 0. On the right, you get 0. Of course, the square root of 0 is 0, and the right-hand side is 0. So certainly 0 equals 0 is a true statement. Therefore, we declare that our solution candidate, x equals negative 1, is indeed the solution to our radical equation up here. And we go on to the next question. Let's look at Q8, same sort of idea. Solve and verify. Do not forget, I believe that this is exactly the same as the one we just... No, it's not. I thought it was, but it's not. But anyway, sorry about that. Solve and verify. Do not forget to verify. Okay? So here's our little standard form that I started out with in the very, very beginning. Let me go back to the very, very first slide here. Okay, do you remember this was standard form? And finally, we got standard form here. And let's see where it is. Right here. Okay, we identify that capital A is 1, the capital B is x, and the capital C is 1. And notice that 1 dot 1 is positive, so we already know there's no solution. Okay, but anyway, we'll go along for the ride anyway. The first idea is to transpose that 1 over to the right-hand side, leave the radical on the left. At that stage, you want to square both sides, so we'll go ahead and square both sides. But again, the note. Left-hand side is greater than 0. The right-hand side is less than 0. That implies no solution automatically. But again, we'll play dumb over here. We'll go along for the ride. We're going to go ahead and square both sides. On the left we get x. On the right, -1 all squared is 1. That's our solution candidate. And then we're going to verify that the left-hand side is equal to the right-hand side. So we go up here to the original equation, we drop it down, and we substitute in x equals 1, which was our solution candidate. When we sub in x equals 1 here, we get the square root of 1 plus 1 equals 0. Of course, on the left, the square root of 1 plus 1 is just 2, and we get 2 equals 0. And as anticipated, that is false, and hence there is no solution. But of course, we knew that from this note up here that there was no solution. Okay, so let's go on to the next slide. Question 9, solve and verify, do not forget. Now this is in standard form, as in the very first slide that I presented. The first thing you want to do is the -4 gets transposed over to the right-hand side. So we have a single radical on the left, and we have a 4 on the right. We're going to square both sides. Squaring the left-hand side removes the radical. We get x plus 3, and then 4 squared is 16. So that's the radical-free equation, and we obtained it by squaring both sides. The next move is to bring the 3 over to the right-hand side to transpose, and then we get x equals 13 as the solution candidate. And again, we need to verify that the left-hand side is equal to the right-hand side. We take the original equation and copy-paste it down here, and then substitute in the solution candidate, which is x equals 13. And then when we do that, on the left-hand side, we get the square root of 13 plus 3, which is square root of 16, and then minus 4, and then equals 0. On the left, we get a 4 minus 4, and on the right, we get 0. Of course, 4 minus 4 is 0, so we get 0 equals 0, which is certainly a true statement, and that implies that x equals 13, which was a candidate, is now in fact a solution. Question 10, same sort of idea. Solve and verify. Do not forget to verify. This equation over here is not quite in standard form, but we'll deal with it anyway. The first move is to transpose the 3 over to the right-hand side. And on the left, we're left with minus square root x minus 5. And then 1 minus 3 is -2. And then we can divide both sides by -1 if we wanted to. That's completely optional. You can go ahead and square both sides at this stage if you want to. No harm done. But anyway, divide both sides by -1 if you want to. When that happens, of course, that removes both negatives, and you get the square root of x minus 5 equals 2. And now it's time to square both sides. When you square the radical on the left, you get x minus 5. When you square 2, you get 4. Now you transpose the -5 over to the other side, and we get x equals 4 plus 5, which is 9. And that's our solution candidate. And then we need to verify that the left-hand side is equal to the right-hand side. Again, we go up here and copy-paste the original radical equation. There it is right there. And we substitute in our candidate, x equals 9, as usual. And we get on the left-hand side, we get 3 minus, 9 minus 5 is 4, so we get the square root of 4. And on the right-hand side, we get 1. On the left, we get 3 minus 2. On the right-hand side, we have 1. And on the left, we get 1. On the right, we get 1. Of course, that's a true statement. And we conclude that our solution candidate, x equals 1, is indeed the solution to our problem. Thanks to all for viewing this video. Stay tuned for many more videos to come. If you liked the video, please give us a like, submit comments, and subscribe to our channel. If not, please tell us how to improve it. Over and out from Ernest at MathLab Tutorials in Toronto.